We're going to start 25 tomorrow, so the plan is finish up 24, start 25 tomorrow, continue 25 on Monday and Tuesday, part of Tuesday. Tuesday we're checking out. And so 25, I'm not really going to follow the book order presentation, and so you should be all right just reviewing your notes for the final. You wouldn't have to necessarily read the chapter. It's a long chapter.
Considering the homework is chapters 24 and 25 you do on the day of the final?
Yeah, 24 and 25 will be due on the day of the final. 25 I'm going to shorten by a few problems. Some of the problems are lengthy calculations. Okay, any other questions? I don't have a practice test for 24 and 25. But your final exam is not going to be like one half chapters 24 and 25 and the other half the rest of the class. It's going to be a few extra questions from 24 and 25. Well, the 24, there's only two sections. There are three sections we need to cover.
Did you say it was mostly multiple choice?
The final exam? Yes.
No actual written?
No, there's written too.
It's mostly multiple choice?
Yeah. The written, I think I already told you what's going to be on the written. Did I?
Probably so.
No?
Like what type of problem?
Yeah.
There'll be a bit of like extra credit or something, right?
Right, that's true.
Yeah, I think I remember that. I don't remember this credit.
Did I tell you about how many multiple choice problems there are going to be?
60?
60 is correct, and then you're going to have some written stuff. In the written stuff, you actually have 3 homework assignments due on the day of the final. And 24, 25, and the chemical reactions. And on the final exam, you're going to have some chemical reaction problems that you need to predict.
Predict off the top of our heads or with charts?
With charts.
The chart
Yeah.
given to us.
Yeah, I'll give you the chart. Redox chart and the acid-base chart. And so that's what the written part of the final is going to be.
Just that.
Just that.
Written is just chemical reaction.
Just chemical reactions, right.
How's your chicken exam?
It was good. How's yours?
It's good. I got the border spicy.
Nice.
Very nice.
Okay. Well, anyway, the final exam is not going to be, like I said, heavily biased towards 24 and 25. You're just going to have some extra questions. Did I say about how many questions there were per chapter?
No.
Well, you can figure it out, because if there are about 60 questions, that's going to give you about how many questions per chapter.
5 or 6.
Yeah, like 5 to 8 questions, and so let's see. You might see a few extra questions from chapter 20, something like that. Somebody was asking about how to prepare for the final, and so if there are 5 questions on the final per chapter, then you would think, what were the most important concepts and what were the most important calculations, and work on those. Another thing to do is to go back and review all the multiple choice questions that you had before. The multiple choice questions on the final will be similar to the multiple choice questions you've had.
Considering the chemical reactions handout that we're going to turn in, it just says to balance the equations. Is that all we need to do?
The last 5.
Last 5.
Yeah, you have 20 questions on that, right? Each one's worth a half a point.
Okay.
And so the last 5 are...
Wait, so last 5 we need to do like the net ionic equation as well?
No. No, well, those are skeleton redox, so you end up with the net ionic equation when you follow the rules for skeleton redox. I think we did a couple of those in class. Right. a couple of them from the homework assignment. Take a look. Okay, anything else?
When do you think we'll get a 19, chapter 19 test back?
So it's looking like Thursday. I'm going to give that back. 19 on Thursday, and then my plan is tomorrow I'm going to give back the. Well, today I will give you back your qualitative analysis and a rough draft if you turned in a rough draft. And then Thursday. Actually, no. Tomorrow, your synthesis lab. I'm going to give that back to you. And the exam 19 on Friday. I haven't had a chance to update the grades. I'll update the grades coming up. So, a lot of people were asking about that. I haven't updated the lab grades. I don't think I've entered any lab grades yet. Lab is either going to help you or hurt you. Because some of the labs are just, if you were absent for that particular lab and you didn't make it up, it's going to hurt you. But if you're present, some of the labs, like today's lab, I'm not going to collect anything for today's lab. I'm just going to check attendance. That's it.
Did you lay it out, like, for the lab grade? Like, how much of it is participation, how much of it is, like,
No.
normal papers?
For example, today's lab is 100% participation. Some of the other labs, the report counts for a lot of your grade. But all the grades, all the labs have some participation. So even if you didn't turn in any report, but you were here, I'll give you some points. You aren't going to get a 0 for not turning in.
And it's basically kind of like every level, like 15 points on it, right? It's like more like
Right. The formal reports are worth 30 points, double. The qual's worth 35 points because we just had so many weeks of that lab. So it's worth a little more.
Part of that 35 points was whether you came to class or not.
Right. Part of that 35 points was it's part of the 35 points is just coming. And so the reason is let's say somebody fails to turn in a report for that. Well, I'm not going to give them a 0 if they came and did some of the work. I'll give them some points. Not that much, though.
Like 5 out of 35.
No, actually,
Less.
depends on the lab. On the qual, it's like if you came to, well, maybe it's like that, 5. Maybe it's less. 1 or half a point.
So like we should be
No,
like,
this is just a joke.
so we shouldn't be like worried when we get like a 30 out of 35 when we start grade, right?
What's that?
So then we shouldn't be like worried if we only see like 30 out of 35 when we get our lab report back. That has all like the participation.
No, there's no participation points added to that, so
Oh.
that would be just 30 out of 35.
Got it.
Yeah, there is one grade called lab technique, right, that is incorporated in there. The lab technique is just for it's just for people who have really bad lab technique, that is, come ill prepared or leave a mess all the time, that kind of thing.
Like individuals that can stress different things, putting the technique up there. Isn't a lot of
Lab technique isn't like, oh, I got a 50% yield. 50% yield, that's okay. I wouldn't worry about that.
Isn't there a portion of the formal paper where you describe kind of like how you perform the experiment itself? Other than just reading off. I mean, you can do more than just read off.
Well, in the formal lab report, you have those sections: abstract, intro, and discussion. What you're talking probably is the experimental section.
Yeah.
Experimental section is you just talk about what you did. In the discussion, you might talk about technique type issues.
Yeah, so like for example, someone got like better yields. And then,
If somebody got better yields, that doesn't factor in at all.
okay. I mean,
Unless the purpose of the lab was to get maximum yield. Like for example, if you go to organic chemistry, then you'll be graded on yield, for certain labs. There's certain reactions because of side reactions that occur or because of equilibrium processes, it's impossible to get 100% yield. Doing it the way you would do it. You'd have to tweak it to get 100% yield. That is, you'd have to do Le Chatelier's shift. And so in a lot of organic synthesis, your typical yield is 60%, 70% yield. If you're getting a 60, 70% yield, that's actually considered good. In a lot of quantitative analysis, 60 to 70% yield is bad. Like for example, if you're doing the sulfate analysis in Chem 1A and you got a 60 to 70% yield, then you got some pretty bad numbers for that. And so for the synthesis, I know some people mentioned that they're talking about losses. They got, let's say, 80% yield or something, and they're talking about bad technique or losses. Or I see 80% yield for a synthesis lab like that is good. I don't think that's bad at all. Okay. The problem is when you do multi-step synthesis, if you get an 80% yield on each step, it's compounded. So by the fifth step, how much have you lost? A lot. So much so you might not be able to continue.
16%.
All right. Other questions?
what are we doing in lab?
Can you post the keys for all the tests that we don't have on Piazza?
The keys for the exams you took?
Yeah. Because there's some of them that aren't on.
Yeah. I need a reminder, and then I'll sort of post those. Okay. Anything else? We'll get started. Did we talk about this already?
Yeah.
What's this all about?
Basically how they come in contact with the orbitals, some repulse to repel.
Okay, are the d orbitals participating in the bonding?
No.
What do we call those d orbitals or d electrons?
Non-bonding.
Non-bonding. So everybody's clear about that, right? These are non-bonding electrons stuck in the middle of the energy level diagram. And when the blue things, what are the blue things?
Electron, ligands.
Ligands. When the ligands come in, they're donating electron density, and there's going to be some repulsions. And which of these orbitals will be repelled the most, or will experience the strongest?
A and B.
Yeah, A and B. And so that results in what we call
Something energy.
a splitting
Kill you.
of the orbital energy levels. The d orbitals used to be degenerate, and so you draw 5 lines to represent 5 d orbitals. But now they're going to be split, and so these non-bonding orbitals are split so that these two, A and B, are now higher in energy than C, D, and E. Here. And this splitting is the origin of the optical and magnetic properties of these complexes. The optical properties are a result of this. The splitting energy here, the gap, is usually in the visible region of the electromagnetic spectrum. And so if I want to promote an electron from a lower energy to a higher energy orbital, it's got to absorb a visible photon. when it absorbs a visible photon, then it doesn't have the complete rainbow, and you get some net color that results. So, for example, if somebody, or if something, or some atom, or some electron absorbs the green photon, do you know what color it appears?
Red.
Red. And so that gives it color. So chlorophyll must be absorbing what? Red. Well, chlorophyll is a little bit complicated because it absorbs different. The degree of splitting is going to depend on the ligand. You know, how much electron density is donated over there. And so we look at these. Not all of these are going to be the same as far as negative charge density donated to the central metal. And not all of these are going to have the same degree of repulsion. And so the things that are very strong ligands, like cyanide, carbon monoxide, have carbon as the donor. Carbon as the donor, it's going to have a lone pair on the carbon atom, and the negative charge goes on the carbon. When you look at cyanide, it looks like the negative charge is on nitrogen. That's wrong. The negative charge is actually on carbon. It's the carbon that's attacking, and so that leads to a very strong electric interaction, which leads to a strong electric field. So we call these strong field ligands, and the net result is a large splitting. The splitting we call delta, and the O just stands for octahedral. So we generate a large octahedral splitting energy there. So we got carbon donors and then nitrogen donors, nitrite, ethylene diamine, pyridine, ammonia. Then we have oxygen donors like EDTA. We're going to skip the nitrogen and the sulfur donors. And so we're just going to memorize this. Carbon donors are the strongest, followed by nitrogen donors, followed by oxygen, followed by the halogens. And that's the pattern you want to remember.
Strongest to weakest?
Strongest to weakest. It goes carbon, nitrogen, oxygen, and then the halides or the halogens. So what happens is that alters the gap, because over here, if we have a halide, we get a small gap or a small split. Over here with cyanide, we get a large gap or a large split. Oh, we can see that here. Fluoroligands are what we call weak field. Weak field ligands have a small split compared to amine. Amine would be a stronger field ligand, and it would have a larger split in energy. Well, the gap here, the splitting energy is going to be important for magnetic properties, because if you look at these, both of these have cobalt. What is this one called? This is hexafluoro cobalt or cobaltate. Hexafluorocobaltate, and the charge on cobalt is +3, -3. It's +3, so it's going to be cobaltate 3. So that's cobalt 3+. How many d electrons does cobalt 3+ have? So do you remember the trick with using this? Cobalt +1, +2, +3. D6. And so it has 6 d electrons. You can see them here. Okay, over here, this is the mean. It's going to have a bigger gap here. And this is cobalt. Let's see. This would be hexaamine cobalt or cobaltate? Cobalt, Roman numeral 3. And so this is also cobalt 3 with 6 d electrons. But take a look at these 6 d electrons versus these 6 d electrons. Do you see the difference in the filling pattern here? Normally we'd fill it like this. You fill the lowest energy orbitals first. That's called the off-bow principle. But for complexes, we might violate the off-bow principle. Do you know why? The reason why is because of the splitting energy.
The splitting energy and the pairing energy are somewhat comparable. Pairing energy would be how much electron repulsion, electron-electron repulsion you have when you pair electrons into a single orbital versus leaving them singly occupied. There's no electron-electron repulsion with two electrons in the same orbital here. And so what we end up with is two different filling patterns. One filling pattern we call high spin. The high spin, the reason is because it has more unpaired spins usually, not always. Sometimes it has the same. Over here we call this low spin, less unpaired. And so this is called a high spin complex. This is a low spin complex. So strong field produces low spin. Weak field produces high spin. Weak fields produce high spin because of this. There's some energy associated with pairing electrons. And so when we fill this, we go 1, 2, 3. Now the fourth electron can either be promoted up here or paired down here. It turns out the fourth electron here is promoted. The reason it's promoted is because the energy required to pair the electron is greater than the energy required to promote the electron because the gap is not big. And so we end up with something like this where if I look at this, I go 1, 2, 3, and I go 4 here. 4 because the pairing energy, which I'm going to just label P, is greater than the splitting energy, which I'll label delta O. This is why it's called high spin, because now we're putting an unpaired spin in a higher energy orbital. And so we're going to have more unpaired spin, so high spin. So that's 4. Then the fifth one is going to go here. Now the sixth one we have to pair. And so we're going to pair a lower energy orbital like that. And so this results in 1, 2, 3, 4 unpaired spins or unpaired electrons.
What did you say delta O represents it?
Delta O represents the splitting energy. Delta O is the gap here between these 3 and these 2. The energy gap. Over here, this is strong field, so delta O is bigger now. And so in this case, what happens is rather than promote it, we're just going to pair it because the splitting energy is greater than the pairing energy. And so what results is, in this case, no unpaired electrons. So this would be a diamagnetic, and this would be highly paramagnetic, even though they both have 6d electrons. It just depends on the ligand. And so the magnetic properties are totally different between these two. The optical properties will be different as well. The optical properties are how they interact with light. And so over here, if I want to promote an electron from down here up to there, it has to absorb a photon of light. Same thing here. I need to absorb a photon of light. Well, over here, I can absorb a lower energy photon because I don't have to promote it as high. Over here, I'd have to absorb a higher energy photon to promote it higher. And so tell me, what is low energy visible light? Red, orange, yellow, or green, blue, violet?
Red, orange.
Red, orange, yellow is low energy. And so over here, I absorb red, orange, yellow. If I absorb red, orange, yellow, some color in there, then let's say if red is absorbed, if something absorbs red, what color does it look like? Green. And so this complex might look green, it might look blue, it might look violet because it's absorbing lower energy photons. Over here, I absorb higher energy photons, like if something absorbs green, what color does it look like? Red. And so these complexes are red, orange, yellow because they're absorbing higher energy photons because of the bigger gap here. And so that's the optical and magnetic properties of these two complexes here. All right, here we're looking at a tetrahedral field. Okay, and so we got to imagine, you see these points are where the ligands are coming in. And so can you take a look at this? And if you look at the XYZ quadrant here, the ligand is coming in, between the three axes here, right in the center of X, Y, and Z. Do you see that?
Yeah.
And so do you see how it's coming into the quadrants here, here, and here? And so now what you want to do is you want to go back here. And then visualize where they're coming in. Here, 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 and then see how they're going to interact with these particular orbitals. And so check that. Be right back.
This stops in color.
Why do you think it's one
That's what he says.
I know, exactly.
I laugh.
That's how the word is
Hey, Jonathan.
What's up?
You,
It's like things like that.
well, do you want to
I can
start
lick my elbow.
What?
Yeah, that's
What do you need?
Yeah.
What did you
Oh. Yeah, maybe more next week.
So I'm thinking like this.
I was dropping a little boring here.
I still, you do have very good.
Yeah, I was already.
What
Am I doing it all?
I feel like this week should be more of like,
I tried to set up a graph.
all they have to do is keep really stretched.
So you know the time equivalence factor, right?
Yeah.
So that's basically our P.
Like, hey,
So find the pKa that matches the unknown. And then we'll figure out the K that matches your
Okay, so what did you guys come up with? Which orbitals will it tetrahedral in other words, does this ligand go directly into any of the lobes of any of those? No. And so what that means is that the ligands do not repel directly into a lobe so that the interaction isn't as strong. And so the first thing is the tetrahedral splitting energies are a lot smaller than the octahedral splitting energies, because octahedral, some of the ligands went straight into a lobe, others went between the lobes. In tetrahedral, all the ligands kind of go between the lobes. And so if we do a geometry calculation, basically we can calculate it. A tetrahedral field is going to generate only 4/9 the magnitude of the octahedral field, 4/9 being about 0.44. Okay, the next thing is this. Well, it doesn't go straight into any lobes, but it'll interact with some lobes more than others. And so if I look back at the d orbitals, what orbitals will it interact most with? It's going to interact most with the ones that are between the axis, because these are coming in between the axis. And so the ones with the lobes between the axis are the xy, xz, and yz. The ones with lobes on the axis are the z squared and x squared minus y squared. And so what we see is an inverted pattern. And so two things about tetrahedral. One, it's upside down octahedral, right? And two, the gap is small. And so what that means as far as the gap goes is this. Go back here. What it means about the gap here is that all tetrahedral complexes have a small delta, and all of them are high spin. That is, delta is smaller than the pairing energy, so we always promote rather than pair. So that's tetrahedral.
Wait, what instead of promote?
We always promote rather than pair. And so all tetrahedral complexes are high spin. High spin means put the electron in a higher energy orbital rather than pairing it. That's tetrahedral. The next one we're going to look at is square planar. And so we look at square planar as bringing a square planar arrangement of the ligands right on the axis, plus x, plus y, minus y. And so if they're coming right on the axis, then the d orbitals with lobes right on the axis are going to be impacted the most, especially the ones with lobes on the x-y axes. Well, there's only one with lobes on the x-y axis. That's going to be x squared minus y squared. And so this one's impacted. And then the xy's are going to be impacted because those have lobes in the xy plane between the axis. And then the z squared has that little hula hoop around the axis, right? And then these other two aren't going to be nearly as impacted because the xz has lobes in the xz plane and the yz has lobes in the yz plane. And so we get a splitting pattern that looks like this, a 2, 1, 1, 1 splitting pattern. You know, these three are kind of clustered here. But square planar complexes have fairly large splits. If you look at delta square planar, it's 1.7 times the octahedral, which means that the square planar are always low spin. And so just to summarize now, square planar are always low spin, tetrahedral are always high spin, and octahedral depend on the ligand. Strong field ligand means octahedral is low spin, right? Weak field ligand means high spin. Good. All right, so let's look at some of the homework problems for this. In fact, let's look at all the homework problems. There aren't that many homework problems for crystal field theory, so it won't take very long to go through them all. So let's look at number 17 first. Describe how the crystal field theory explains the fact that so many transition metal compounds are colored. So where does a color originate in a lot of these complexes or compounds? Well, what absorbs visible light? Electron transitions. So electron transitioning from a lower energy orbital to a higher energy orbital. And it turns out that complexes will result in a splitting of the d orbitals so that the light or the gap is in the visible range. When you look at the rest of the MO diagram, the gaps are kind of big, and so they're going to be in the bigger gaps are going to be in the UV range, right? And so because of having these d orbitals being split by the electric field generated by the ligands, we get colors. Not all transition metal complexes are colored. So, for example, if we were looking at zinc 2+, you know zinc 2+ is not colored. What is zinc 2+ in complexes? It's colorless or white. A lot of zinc salts are colorless or white, like zinc hydroxide. Whereas copper hydroxide is colored. Can you tell me why? Well, I'll tell you why. Zinc has how many d electrons? Well, count it. Zinc, 2 plus, plus 1, plus 2. 10 d electrons. 10 d electrons means what? It means it doesn't matter if it's high spin or low spin because all the orbitals are going to be full. Now look, if a photon comes in here, can it bump it from this orbital to this orbital, an electron? No, because that would violate the blank exclusion principle. What's the blank exclusion principle? The Hund's exclusion principle? The Heisenberg uncertainty principle? The Pauli exclusion principle. Well, we can't have more than 3 electrons in one orbital, so. D10 complexes are colorless. So zinc and cadmium should form white compounds or colorless compounds, right? Likewise, titanium plus 4. Titanium 4 oxide is used as white pigment. Why? How many d electrons does titanium plus 4 have? 0. Right? Plus 1, plus 2, plus 3, plus 4 gives me 0 d electrons, which means that, I have some d orbitals here, but what am I missing? Yeah, there are no electrons in there. And so if I have titanium plus 4, then the only transition that's going to occur is the one at the top of the whatever valence, all the way up to the conduction, which is probably going to be UV. So it should be colorless. It'll be titanium 4 oxide. Okay, 18, cyano complexes. Okay, cyano, strong field or weak field? Strong. Yeah, cyanide, strong. Cyano complexes of transition metal ions such as iron 2 and copper 2 are often yellow. So, if a cyano complex is yellow, what color light must it be absorbing?
UV.
No, not UV. Well, yeah, you guys know this, right? Red, orange, yellow, green, blue, indigo, violet. So if it looks yellow, it must be knocking out violet. And so it's got to be absorbing violet light, and the rest of the colors result in yellow, or average out in yellow, or whatever you want to say. It has to do with the waves. That makes sense because, a big gap means higher energy light has to be absorbed. Violet is right on the edge of ultraviolet, right? So violet's high energy, it's going to be able to promote an electron over the big gap. So that makes sense. Whereas aqua complexes, aqua, is that strong or weak? It's on the weak side. A weak ligand means a smaller gap. A smaller gap means absorbing lower energy light. And so whereas an aqua complexes are green, well, if it's green, what color is it absorbing? Red or blue? Yeah, if it's blue, it's absorbing orange. Explain the basis of the difference in color. The basis of the difference in color depends on what the energy gap is. The crystal field splitting energy, they call it. All right, 19. If the ion cobalt 2 plus cobalt 2 plus, how many d electrons does cobalt 2 plus have?
7.
Plus 1 plus 2, 7. If the ion cobalt 2 plus is linked with strong field ligands to produce an octahedral complex, the complex has 1 unpaired electron. And so it's octahedral. The splitting pattern for octahedral is 3, 2. We have 7 electrons. 1, 2, 3. Where's the fourth? Fourth, should I do high spin or should I do low spin? High spin, low spin. I should do low spin because it's strong field and the gap is big. So that's 4, 5, 6, and then the 7th I have to promote. No other choice. And so when it's linked to a strong field ligand, the complex has 1 unpaired electron. Yes, it should have 1 unpaired electron. If cobalt 2 plus is linked with weak field ligands, the complex has 3 unpaired electrons. So if we do weak field, the gap is a lot
Closer.
Yeah. And so now I go 1, 2, 3, 4. Well, actually, I got to ask the question: high spin or low spin? High spin. It should have gone high because the gap is small, and the pairing energy is likely greater than the gap energy or the splitting energy. And so that's 1, 2, 3, 4, 5. Now I have to pair, so I better pair a lower energy orbital. 6, 7. So if cobalt 2 plus is linked with weak field ligands, the complex has 3 unpaired electrons. And that's right, 3 unpaired electrons. 1 down and 2 higher. How do you account for this difference? Well, you account for the difference based on high spin or low spin in the gap, right? And so in other words, the pairing energy versus the gap energy or the promotion energy. Okay, number 20. In contrast to the case of cobalt 2 plus, considered in exercise 19, no matter what ligand is linked to nickel 2 plus to form an octahedral complex, the complex always has 2 unpaired electrons. Explain this fact. And so what's the difference between cobalt 2 and nickel 2? So let's take a look at nickel 2 plus in an octahedral complex like this. So nickel has how many d electrons? D8. And so let's just fill these in. This is 7, so an 8 is just 1 more electron here. So I get 2 unpaired electrons here when we're looking at nickel 2 plus, D8. Over here, I end up with 2 unpaired electrons. And so the magnetic properties are the same, regardless of the ligand. So I could have a strong field ligand here, it's going to have 2 unpaired electrons. Weak field ligand here, it's going to have 2 unpaired electrons. So the same. A. Predict which of the complex ions. How would you name this? Hexachloro molybdenum. Molybdenum. Okay. Molybdenum or molybdenate? Molybdenate. 3. Good. And so we're going to compare this. Well, the molybdenum has got to be in the +3. It's octahedral. This is a chloro complex. So molybdenum plus 3 has how many d electrons? So 1, 2, 3, so it's 3. So molybdenum plus 3 is what we call D3, D3 ion. It's octahedral. So we're going to have a 3-2 split pattern. And is it strong field or weak field? Chloro. Chloro is weak. And so let's fill it with electrons. 1, 2, 3. For molybdenum 3 plus, we didn't really have to worry about pairing or promoting because there are only 3 electrons. If we have 3 electrons, we don't even have to finish this. It says one is diamagnetic, the other is paramagnetic. If you have an odd number of electrons, you can't pair it, right? And so this has got to be paramagnetic. But let's finish this anyway. How would you name this? Tris ethylene diamine cobaltate or cobalt? Cobalt 3. And so cobalt 3 plus is the central metal, and that has how many d electrons? The cobalt 1, 2, 3 is d6. Is that a strong field or weak field? Ethylene diamine. Strong field, so big splitting. And so I got 6 electrons. 1, 2, 3. The 4th one, pair, because promoting is too much energy. 5th one and 6th one. And so which one is diamagnetic? Cobalt 3. Which one's paramagnetic? Molybdenum. B, the number of unpaired electrons expected for the tetrahedral complex ion. How do you say that? This one here. Tetrachloro. Cobalt 8. 2. So that's cobalt 2. Cobalt 2 plus is D. Cobalt plus 1 plus 2 is D7. This is a tetrahedral. Tetrahedral is an upside down octahedral. The gaps in tetrahedral are all relatively small. This one's going to be especially small because if you look at the ligand, is the ligand strong field or weak field? Weak field. The weak field should lead to a small gap. A strong field is going to make the gap bigger, but even with the strongest ligand like cyanide, does tetrahedral form low spin? No. Tetrahedral never forms low spin. Tetrahedral are all high spin, no matter the ligand. So D7, 1, 2, the third one's going to be promoted, high spin, 4, 5, 6, 7. So how many unpaired electrons are predicted? 3. Number 22, predict A, whether the square planar complex ion, how would you say that? Tetra, PY stands for pyridine. So would you call it pyridino or just pyridine? Pyridine. Just pyridine. Tetrapyridine, copper, 2. Is diamagnetic or paramagnetic? You know, predict whether it's diamagnetic or paramagnetic. And so, this is square planar. So we got copper 2 plus, which is D9, correct? D9. And what's the square planar split pattern? 2, 1, 1, 1. And square planar are all low spin or high spin? All low spin. So 1, 2, 3, 4, 5, 6, 7, 8, 9. One electron in the highest energy orbital. Is it diamagnetic or paramagnetic? Diamagnetic or paramagnetic? Para. It's para. You know what? You don't even have to do this. Why? Because an odd number. Can you pair an odd number of electrons? No. So you can save time. Didn't have to do this.
It's only when it's even that you have to figure
Yeah, when it's even, then it could be paramagnetic or it could be diamagnetic. Yeah, that's when we got to figure it out. But odd number, it's always paramagnetic. B, whether octahedral, how did you say this on?
Manganate.
Yeah, hexacyanomanganate 3. And so, in other words, is magnesium 3 plus is the central metal, which is D. It is those are manganese. Sorry, manganese. 1, 2, 3, 4. D4. So what are they asking for here? Octahedral. All right, so this is octahedral. Is that a strong field ligand or a weak field? Cyanide. Cyanide is strong field, so big delta. And let's fill them with electrons now. D4. 1, 2, 3, 4. This is paramagnetic. Now the other complex is this one here. How would you name this? Tetrachloro ferrate 3. So tetrahedral. This is iron 3 plus. How many d electrons does iron 3 plus have?
5.
D5. And tetrahedral are all high spin. And so the gap is small. So we go 1, 2, up, high spin, 3, 4, 5, 6. So the question is, which one has a greater number of unpaired electrons? Yeah, the tetrachloroferrate 3. In example 24-5, we chose between a tetrahedral and square planar structure for tetracyanonickelate 2 based on magnetic properties. So, going back to that particular example, if I have a nickel with 4 cyanos, I want to know the structure. One structure, this could be tetrahedral. Tetrahedral, I'd have a nickel here. How many valence electrons does nickel 2 plus have? Well, nickel here has the electron configuration argon, 4s2, 3d, 8. If nickel loses 2 electrons, I form nickel 2 plus. Are the 2 electrons lost from the 4s, or are the 2 electrons lost from the 3d? From the 4s, the higher the end. So I lose 1, 2, I lose all those, and that leaves me with 8d electrons. But those 8d electrons, are those considered valence or are those considered core electrons? Core. And so to answer the question, how many valence electrons does nickel 2 have? 0. It's not going to contribute any, because the electrons are inside the core, the D. But the ligands come along, and the ligands are going to be donating both electrons to the central metal, because that's what these Lewis bases do. They donate a pair of electrons. So I get a cyanide there, cyanide here, and a cyanide here. And then what? Okay, that's one possibility. The other possibility is this. And that is, I have my nickel 2 here, and I'll have a square planar arrangement of cyanides. Like that. So which is correct? Using Vesper valence bond theory, you'd predict that tetrahedral is correct. You have 4 bonded atoms and no lone pairs, right? Over here, you have 4 bonded atoms and no lone pairs. Normally, to generate a square planar structure, you need a lone pair on top and a lone pair on the bottom of this, but here we don't. And so based on Vesper, this should be correct. Okay? It should be. But does Vesper work for transition metal complexes? No. And so we don't even consider Vesper. Instead, what would work here is to look at what happens. If it's tetrahedral, it has a splitting pattern like this, and nickel 2 plus is D8. 1, 2, high spin, 3, 4, 5, 6, 7, 8. And so you end up with 2 unpaired spins here. If we do square planar, we have a splitting pattern like this: 2, 1, 1, 1. It's low spin: 1, 2, 3, 4, 5, 6, 7, 8. So in terms of magnetic properties, you can tell the difference. If nickel adopted a tetrahedral geometry, then there would be 2 unpaired spins, which can be detected experimentally. If nickel adopted a square planar, it would be diamagnetic. And so this would be repelled by electric fields. This would be attracted to electric fields. So which is it? It is square planar. And how do you know it's square planar? Because experimentally, the complex is diamagnetic. The complex is not paramagnetic. So that's how we'd be able to figure that out. So magnetic properties would prove it. And so why would nickel 2 adopt a square planar structure? Because Vesper is to minimize energy, right? Vesper, you try to adopt a geometry that would minimize the repulsions between the electron groups. And so it doesn't make sense because square planar is not minimizing that energy. And so it turns out that we are minimizing A energy, not the repulsions. We're minimizing the energy of these non-bonding d electrons. When you look at this here, all the orbitals are occupied. We have 4 electrons in the lower energy set, 4 electrons in the higher energy set, and they're just going to average someplace here. Over here, when you look at it, we're going to have these 4 electrons in the lower energy and this in the higher energy, but the highest energy orbital will be empty. And so if we average all the energies of the electrons here, and all the orbitals are filled, we're going to get something around here. Whereas if we average all the energies here, we're going to get something lower in energy because the highest energy orbital is empty. And so we don't even have to factor that into the average. So the average is going to be these lower energy orbitals here. And so does that make sense for nickel 2? Nickel 2 likes to form square planar complexes when it's 4 coordinate. And so nickel 2 forms square planar complexes. What about platinum 2? Platinum 2 plus is D8. And so for platinum, then we expect the same result as with nickel. All right, now let's try to apply this to a different system here, and that is determine whether we can tell the difference between octahedral and tetrahedral amine complexes based on magnetic properties. And so here's the tetrahedral nickel 2. But if we had the octahedral nickel 2 with a strong field ligand, that strong field, yeah, ammonia, we get a large split, this. And so if we have nickel 2 plus, this is D8, we go 1, 2, 3, high spin, 4. Actually, did I get that right? Do we do high spin with cyanide? No. Do we do high spin with amine? No. Do we do high spin with O? Yeah, probably. With Cl, Br minus? Yeah, probably. And so here, this should be low spin. This is D8, so 1, 2, 3, 4, 5, 6, 7, 8. And so, right. Yeah. So when I look at this electron configuration versus this one, can I tell the difference in magnetic properties? Actually not, because both of them are going to have the exact same number of unpaired spins, which will be 2 spins here and 2 over here. Okay, 24. In both, how do you say this one? Hexa aqua, iron 2, and hexacyano, ferrate 2 ions. The iron is present as iron 2. How many d electrons does iron 2 have? 6. However, hexa aqua iron 2 is paramagnetic, whereas hexacyano ferrate 2 is diamagnetic. Explain this difference. Yes. And so we have iron 2, which is D6, and then we have octahedral with a fairly large splitting energy. This would be which complex, the cyano or the aqua complex? This is the cyanide complex. And then we have one with a smaller splitting energy, which will be for the aqua complex. D6, here, 1, 2, 3, 4. High spin or low spin? Low. 5. 6. And so the cyanide with the iron tube leads to a diamagnetic complex. Okay, now with aqua, we're going to get high spin, so we go 1, 2, 3, and then ask ourselves high or low, high spin, 4, 5, 6. And so which one's paramagnetic, which one's diamagnetic? The aqua complex is, and the cyano complex is diamagnetic. Okay, let me one final. All right, one last problem, and then I think we covered all of them for crystal field. 83. Of the complex ions, this is hexa-aqua-cobalt 3 or tris-ethylene-diamine cobalt 3. One has a yellow color in aqueous solution, the other has a blue. Match each ion with its expected color. State your reasoning. And so is the hexa-aqua yellow? Or is the hexa aqua blue? What do you predict? Hexa aqua versus the trisethylene diamine. Is the trisethylene diamine yellow or is the trisethylene diamine blue? One of these is yellow, the other's blue. The ethylene diamine is blue, and the aqua is yellow. Okay, that's all right. Why is that?
Because the aqua requires a lower energy to move up.
Yeah, the aqua weak field requires a smaller energy to promote, and so it should absorb. Well, blue's absorbing what color? Orange. And so it should absorb orange and appear blue, so it absorbs lower energy light, opposed to red. Whereas this one must be yellow, because yellow is absorbing what? Violet. Yep. And so that makes sense because ethylene diamine is a stronger field ligand, which means it requires higher energy. And so this absorbs violet, this absorbs, what did we say? Orange. And state your reason for doing so. Well, the reason would be the weak field ligand versus a strong field ligand and the splitting energy associated with that. All right, so we're going to stop here and then we'll start the next section /lab.